Hi guys. In part one of the performance exam review, we will be talking about the mole and stoichiometry. I know it's everybody's favorite, actually it's mine. So we're going to take a look to start with at the mole, and we're going to work through a couple of these problems and make sure that we understand what it is that we're supposed to do. So let's start from the very beginning, because it's a very good place to start. At the beginning, fill in the conversions. 1 mole is equal to blank particles. Well, this would be Avogadro's number, 6.02 times 10 to the 23rd power. And remember, that was Avogadro's number. And 1 mole is equal to blank, and we're given a little hint here, in grams. So when we're talking about the relationship between moles and grams, we're talking, of course, about molar mass. Speaking of molar mass, moving on to the next part. Calculate the molar mass for the following compounds. We have 4 different compounds here. We have to calculate the molar mass of each one. Well, if you take a look, you're given these things as words, which means that you've got to actually write a formula for each one of these. So let's take a look. Copper 2 chloride. Well, you know that copper is copper. Chlorine is Cl. Well, just a reminder from first semester, this 2 in the copper 2 chloride tells me that copper here has a +2 charge. And we know that chlorine always has a -1 charge. So when the 1 comes here and the 2 comes down here, and there's our formula for copper 2 chloride. So now we have to, now that we know how many of each type of atom we have in copper 2 chloride, let's calculate a molar mass for that. Well, we have 1 copper, and that 1 copper is 63.55 grams. And then we have 2 chlorines, and each chlorine is 35.45 grams. Well, 1 times 63.55 is 63.55, and 2 times 35.45 is 70.90. Well, when we add those up, we get 134.45 grams as our molar mass for copper 2 chloride. Coming down to B for bromine. Well, wow, bromine is just an element. So why would we have this here? Well, you know that when you have bromine all by itself, it is actually not just Br, but it is Br2, because it is one of those diatomic molecules in the periodic table. Remember all of the gens: hydrogen, nitrogen, oxygen, and all of the halogens. So all of the gens are diatomic molecules. All of the gens are diatomic molecules. So here we have 2 times the molar mass of bromine, which is 79.9. Well, 79.9 would give us 159.8 grams. All right, coming up here to potassium sulfate. Sulfate. We know that that's going to be on the back of our periodic table because it's a polyatomic ion. Potassium and then sulfate is SO4. Well, sulfate has a -2 charge. Potassium has a +1 charge. So potassium sulfate is K2SO4. So let's take a look. We've got 2 times potassium. We have 1 times sulfur, and just a reminder, everybody knows that these numbers are coming right off your periodic table. Sulfur 32.07, oxygen 16.00, so it's the atomic masses that are on the periodic table, only these are our molar masses because we're talking about a mole of that particular atom. And then 4 times 16. Well, 2 times 39.10 is 78.20 grams. 1 times 32.07, 32.07 grams. 4 times 16 grams is 64 grams. Add all of those up, and we get 174.27 grams. Then finally, up here at the top, we have aluminum chlorate. Aluminum, and then chlorate. So I have to look on the back of my periodic table, and I find chlorate is ClO3. Well, I'm going to use my pencil for 1 second so that we can just make sure that we make this correct. All aluminum has a +3 charge. Well, when I look at chlorate on the back of my periodic table, I see that it only has a -1. So my 1 comes down here to aluminum, and the 3 is going to go over here to chlorate. Well, you know that when we have more than one of my polyatomic ions, I have to put that in parentheses, and I put a 3 down here. Well, that's going to make a difference in how we calculate this molar mass, and this is a problem that a lot of you still had when we took our moles test and also when we took the stoichiometry test. Alright, so I've got 1 aluminum here. 1 times aluminum. Aluminum is 26.98. Now look over here. Know the 3's on the outside of the parentheses. So that means I've got 3 of that whole thing right there. So I've got 3 chlorines, and chlorine is 35.45. And I've got 3 O3s, which means that I've got a total of 9 oxygens. So 1 times 26.98 is, of course, 26.98 grams. 3 times 34.45 gives me 106.35 grams. And then 9 times 16 is 144.00 grams. Add all of that up, and I end up with 277.33 grams as my molar mass for aluminum chlorate. Alright, now take a look at each one of these. This one is one that I know will give people problems. You've got to multiply this 3 that's outside the parentheses times each thing that's in here. 3 times 3 is 9. 3 times 1, because I have 1 chlorine inside the parentheses, and that would be, so I've got 3 chlorines right here, and I've got 3 times 3, or 9 oxygens, which is right there. Alright, so formula units. How many formula units are in 37 grams of potassium sulfate? Okay, formula units. Now remember, potassium sulfate is an ionic compound, so we can't call it a how many molecules, because it's not a molecule. Remember, ionic compounds are together in formula units, because really that formula is a ratio of how many of this ion do we have for that ion in this compound. So I'm asking for formula units, and I'm giving grams. There's no way that I can go straight from here to here. Well, good thing. What is this? This whole section is about the mole. So I'm going to take 37 grams, because that's what I'm given. 37 grams of potassium sulfate. And I need to change that into moles. So we change this into moles. I need the molar mass of potassium sulfate. So I'm going to put 1 mole up here of potassium sulfate, and then the molar mass of potassium sulfate is 174.27 grams. And I know that because I've already figured it out. That's what that was right there. Well, this is going to give me how many moles of potassium sulfate I have, which incidentally, if you're doing these calculations separately, this would give me 0.2123 moles. But I'm going to go ahead and put another line here and go ahead and finish the calculations in one long row here. Well, now that I have moles, I need to find out how many formula units I have. Well, in every mole of anything, I've got 6.02 times 10 to the 23rd of them. So, and that's how many formula units I'm going to have. So, 37.0 grams converted into moles. Now that I know how many moles, I have 6.02 times 10 to the 23rd formula units in every mole. So now all I have to do is the arithmetic. 37.0 times 1 times 6.02 times 10 to the 23rd divided by 1 times 174.27 times 1. And when I do all of that arithmetic, what I end up with is 1.28 times 10 to the 23rd formula units. So 37 grams of potassium sulfate is equal to 1.28 times 10 to the 23rd formula units of potassium sulfate. Look at the next one. How many grams are in 3 moles of copper 2 chloride? Well, what am I given? I'm given 3.00 moles of copper 2 chloride. And I want to know how many grams are in this. Well, for every mole of copper 2 chloride, I have 134.45 grams. So 3 times 134.45 divided by 1, and my moles cancels out here, leaving me with just grams, gives me 403.35 grams of copper 2 chloride. While we were studying moles, we studied the empirical formula. Okay, remember, the empirical formula is different from the molecular formula in that the empirical formula is the most reduced ratio of elements in a compound. The most reduced, that is, in an empirical formula, I have to take each of the subscripts, and if they will, anything will go evenly into all of them, I have to divide and get the most reduced, like reducing a fraction. However, the molecular formula, on the other hand, is the actual number of each type of atom in a compound. For instance, if I have the compound C6H14, if I have C6H14, this would be the molecular formula. This is telling me that there are 6 carbons and 14 hydrogens in every molecule of this substance, okay, which is hexane, by the way. However, this is not the empirical formula. The empirical formula means that I've got to divide this. If I had a fraction that was 6 over 14, I would have to reduce it to lowest terms. Well, what can go into both 6 and 14? 2. 2 will go into 6 and 14. So that would mean my empirical formula here would for this would be C3H7. So empirical formula, molecular formula. All right, so let's come on down and see if we can finish out this page. Which contains more atoms, 1 mole of helium or 1 mole of neon? Well, neon is clearly a heavier atom, so it must be neon, right? Wrong. It says how many atoms do you have in a mole, or which one has more atoms? Well, if I have a mole of helium atoms, I have 6.02 times 10 to the 23rd moles of, or 6.02 times 10 to the 23rd atoms of helium. If I have a mole of neon, that means I've got 6.02 times 10 to the 23rd atoms of neon. If you had a mole of grapes, you would have 6.02 times 10 to the 23rd grapes. So the answer here would be they have the same number of particles. And I just explained why. Because a mole of anything is equal to 1 mole of anything is 6.02 times 10 to the 23rd of whatever that is. So, if I have a mole of that thing, I have 6.02 times 10 to the 23rd of that thing. Alright, so let's move along to the next page, which is stoichiometry. Alright, so if we are trying to make a determination and write a definition for stoichiometry, we could go back and take a look at the very first set of notes that we took in stoichiometry. And so stoichiometry, is it qualitative or quantitative? Let's think. There are numbers involved, and I'm measuring things based on numbers, so this would be quantitative. So it is the quantitative study of amounts of reactants used. So the quantitative, it is the qualitative study of the amounts of reactants used and the products that are formed. So there's a good definition of stoichiometry for you right there. The quantitative study of the amounts of reactants used and the products formed. On what law is stoichiometry based? Well, if I've got to have the same amount of each atom on both sides of my equation, then we're talking about the law of conservation of mass. So, it is based on the conservation of mass. Alright, so let's get into a couple of stoichiometric problems here. Write a balanced chemical equation for the reaction described below. So here we are again, having to write a formula based on some words here. Strontium oxide. Well, strontium is Sr, and looking at my periodic table, I see that strontium has a +2 charge, and oxygen, so oxide here. Oxygen is an O, obviously, and oxygen has a -2 charge. So strontium oxide is just that. 1 strontium, 1 oxygen. It's going to react with potassium chloride. Well, here's potassium. And then chlorine, Cl. Well, potassium is +1, chlorine is -1, so that cancels out as well. So there are my two reactants. To produce strontium chloride and potassium oxide. Well, strontium, and like I said over here, strontium has a +2, chlorine has a -1, so strontium chloride is SrCl2, plus potassium oxide. Potassium is +1, oxygen is -2, so the 2 comes here, and so there you go. So there's my formula. There's my skeletal equation. So let's see if it's balanced. I have 1 strontium, 1 strontium. So far, so good. I have 1 oxygen, 1 oxygen. So far, so good. I have 1 potassium, I have 2 potassiums. Well, that doesn't work. So I'm going to put a 2 here in front of the potassium chloride. Now I have 2 potassiums, 2 potassiums. I have 2 chlorines, I have 2 chlorines, so I'm balanced. What type of a chemical equation is this? Okay, this particular equation represents the reaction that is a double displacement, or double replacement. So let's see. So I'm going to now be using this equation to work some stoichiometry problems here. Number 9 says, how many moles of potassium oxide will be made from the reaction of 4 moles of potassium chloride reacting with excess strontium. All right, so I want to know how many moles of potassium oxide, and I'm given 4 moles of potassium chloride. So let's start with my given. So my given here is 4 moles of potassium chloride. And I need to change this into, or I need to use my mole to mole ratio in order to figure out how many moles of potassium oxide I will have. Well, I've got moles of potassium chloride on top here, so I'm going to put it down on the bottom here. And I'm looking for moles of potassium oxide. I'll put that up at the top. Now that I've got this written, so I know this has to be on the bottom because I'm trying to cancel this out, which puts the other one, the one that I'm looking for, up here at the top. Now I need to fill this in based on my balanced equation. KCl, I have a 2, so I have a 2 in front of that. K2O, I have a 1, since there's nothing written here, and so there we go. So there's my mole to mole ratio. Well, it's asking me for moles, it's given me moles, so I don't need to worry about grams, I don't need to worry about molar masses, I don't need to worry about any of that. All I have to do is deal with these moles, which means I've got to deal with the arithmetic. 4 times 1 is 4, divided by 2, so that's equal to 2. So this is going to, and moles of potassium chloride cancel out, leaving me with simply moles of potassium oxide. So, how many moles of potassium oxide will be made from the reaction of 4 moles of potassium chloride with excess strontium? And that would be 2 moles of potassium oxide. Look at number 10. How many grams? Okay, so now we're going to have to deal with molar masses, aren't we? How many grams of strontium oxide will be required to make 2 moles of potassium oxide? So this is a grams to mole stoichiometry here. All right, well, what am I given? I'm given 2 moles of potassium oxide. Well, let's first, it asks for grams of strontium oxide, but I can't go straight to grams of strontium oxide. I first need to get the number of moles of strontium oxide. So let's put moles of strontium oxide, and then this is what I'm getting rid of, so we'll have moles of potassium oxide. So now that I know the order that they're going to be in here, let's go up here to the equation. The number that's in front of SRO is a 1. The number that's in front of K2O is a 1. So that means that these two things are reacting in a 1-to-1 molar ratio. 2 times 1 is 2, divided by 1 is 2. Simple enough. Let's go ahead and finish the calculation. It's asking me for how many grams. So when you do this whole calculation right here, that leaves me with moles of strontium oxide. Well, I want grams of strontium oxide. So what I have to do is I have to know what the molar mass of strontium oxide is in order to finish this problem. Well, strontium is 87.62, and of course oxygen is 16. So when I add those together, I get 103.62. So 103.62 grams and 1 mole of strontium oxide. Moles of strontium oxide cancel out, leaving me with just 103.62. So now I can do the arithmetic all the way across. 2 times 1 times 1 point, or 103.62 divided by 1 times 1 times 1. So I don't even worry about my denominator. And 2 times 1 times 103.3, or 103.62 rather, and I have 207.24 grams of strontium oxide. All right, look at number 11. Number 11 says that I have 256 grams of strontium oxide, and I want to know how many moles of strontium chloride will be produced. Well, so now I've got to start with this. 256 grams of strontium oxide. Well, I can't go straight from grams of strontium oxide to moles of strontium chloride. So I've got to change this grams of strontium oxide into moles of strontium oxide. So I have 1 mole here, and the bottom needs to be the molar mass. And the molar mass of strontium oxide is 103.62. That would be 1 strontium, 1 oxygen. Now we can change, once you're finished with this, that's going to give you the number of moles of strontium oxide. Now all I need to do is change this into moles of strontium chloride. So moles of strontium oxide is going to be on top, so strontium oxide has to be on the bottom here, and I'm looking for strontium chloride. And if we look up here to the equation, I've got 1 in front of strontium chloride, and I've got a 1 in front of my strontium oxide. So they react at a 1-to-1 molar ratio. Well, 2.57 times 256 times 1 divided by 103.62, and I end up with 2.47, and that's the number of moles of strontium chloride there are. If you have 256 grams of strontium oxide produced, how many moles of 256 grams of strontium oxide being used, how many grams of strontium chloride are produced, and that, or how many moles of strontium chloride are produced, and that would be 2.47 moles. Finally, in this section, we have 112 grams of potassium chloride, and I want to know what mass of potassium oxide will be produced. Well, 112 grams of potassium chloride. I need to change that into moles before I can do anything else. 1 mole, and the molar mass of potassium chloride is 74.5. In doing this, by the way, that's going to give you about 0.5. That's going to be 0.5 moles. So let's go ahead and finish the calculation because it asks in grams. Let's see. That's gonna give me moles of potassium. That's going to give me moles of potassium chloride. So I first got to, now that I've got moles of potassium chloride, I need to get moles of potassium oxide. So I'm looking for moles of potassium oxide, and I've got moles of potassium chloride. Well, let's look up here at our equation. Potassium chloride has a 2. Potassium oxide has a 1. Okay, so when I do this arithmetic, that's going to give me the number of moles of potassium oxide that I have. But I want to know what the mass is in grams. Okay, so which means that I now need to do one more calculation down here in order to get that. This, if you want to check your work, by the way, up to this point, it is 0.75 moles of potassium oxide. So what we need to do first then is find our molar mass of potassium oxide. And the molar mass of potassium oxide is 94.2 grams. And that's 1 mole. Well, 1 mole of potassium oxide cancels out 1 mole of potassium oxide. And so when I do my arithmetic, remember I just said if if you go 112 times 1 divided by 74.5, that's going to give you 0.75 moles of potassium oxide. Well, moles of potassium oxide times the grams per mole, and what I end up with is 70.65 grams of potassium oxide. So 70.65 grams of potassium oxide are made from 112 grams of potassium chloride. So there you go. There's our quick and dirty review of how to work problems and some concepts with stoichiometry and moles. In part 2, we'll take a look back at solutions, and even though we just did it, we'll also take a look at acids. So stay tuned for part 2.